This is the second part of my lecture on experimental testing. We're going to be looking at hypothesis testing. The process is we start by making a hypothesis, stating the null hypothesis and the experimental or alternative hypothesis, of which we've already looked at some examples. And we've seen that the experimental hypothesis has got to be the exact opposite of the null hypothesis. Then we collect our data and then we analyze it. The way we analyze it is always to test the null hypothesis. We start by assuming that the null hypothesis is true, and we apply an appropriate statistical test which results in a number that's called the test statistic. Then we compare this test statistic with a critical value taken from the appropriate probability distribution. The appropriate statistical test and the appropriate probability distribution will depend exactly what our test is for, and we'll see several examples of these in later lectures. But let's see how we apply a one-tail test. If the yellow curve shows the probability distribution if the null hypothesis is true, which we've assumed it will be, then a value like this one is going to be quite possible because it has quite a high probability. But one down here in the tail is rather unlikely because it's got a low probability. So we can define some critical value such that if the test statistic is greater than this critical value, then it's unlikely to occur by chance. The shaded area to the right of the critical value represents the probability of obtaining either the critical value or a value greater than that. If we're dealing with a two-tailed test, it's a little bit more difficult. Here's again the same probability distribution, and we know a value near the middle is going to be quite possible, but ones towards either tail at the left or the right are very unlikely. So now we have two critical values, and a value of the test statistic more extreme than the critical value in either direction, that is to the right of the upper value or to the left of the lower one, is unlikely to occur merely by chance. So the two shaded areas represent the probability of obtaining a critical value or one more extreme in either direction. Compared with the one-tailed test, the area under the curve is going to be twice that from the one-tailed test, and so it corresponds to twice the probability of the one-tailed test. Now, if we look at this curve and define P to be the area under the tails of the curve, it's the fraction of the area in the extreme tail of the probability distribution. If we're dealing with a two-tailed test, it's the sum of the two tails. If we're dealing with a one-tailed test, it's just one of those areas. It's equal to the probability that a test statistic as big as x, where we've marked x on the distribution, either x or bigger, could be obtained from this distribution just by chance. To actually find the appropriate value, we have to look it up in tables of the appropriate probability distribution. But if we know the distribution, it's tabulated and we can find a test statistic that corresponds to any particular probability or any particular area under the curve. So we can find the critical value in just the same way by looking up the value of x, which gives a suitable probability, and we want a rather small probability. This is known as the significance level, and typically we take a probability of 0.05 or 5% as a suitably small probability to be significant. We'll say a bit more about significance level later. So let's look at how we go about testing the null hypothesis. We start with our experimental question, something that is to be tested, and we formulate two hypotheses, the experimental hypothesis and the null hypothesis. They have to be the exact opposite of each other so that only one of them can be true. In the absence of any data, we don't know which is true. Either the experimental hypothesis or the null hypothesis could be true. So we collect our data and analyze it, and we assume that the null hypothesis is true as a starting point. and we ask, could we get the observed data by chance on these assumptions? If it's quite likely to get our observed data on these assumptions, then we don't have any conclusive result, because the null hypothesis could be true, but then so could the experimental hypothesis. We've done nothing to investigate that, so we're still in that undecisive situation that either of them could be true. But if we get the result that is very unlikely to have obtained the observed data by chance, then there must be something wrong with our assumptions, and we can only conclude that our assumption of the null hypothesis must be erroneous. So we can reject the null hypothesis, and in that case the experimental hypothesis is all that's left. That must be true. This is a useful and significant result, because by excluding the null hypothesis as being very unlikely to be true, then we only leave the experimental hypothesis. But note, if we get the opposite result, that the data is quite likely to have been observed by chance, then we cannot rule out the experimental hypothesis and say the null hypothesis is true, because we know the null hypothesis is likely, but we have no reason to say that the experimental hypothesis couldn't be likely as well. So this is an inconclusive result. It simply means we don't have enough evidence to say either way. The only conclusive result is one in which we can rule out the null hypothesis. How do we interpret these probabilities? Well, if P is the probability of obtaining the given result by chance on the assumption that the null hypothesis is true, then a probability P of more than 0.05 or 5% is taken to be not significant, meaning it's quite possible that these results were just due to chance. We have no reason to reject the null hypothesis. We have an inconclusive result. P less than 0.05 is significant at the 5% level. It means that there's a less than 1 in 20 chance that we could have obtained these results with the assumption that the null hypothesis is true. Less than 5% chance of accepting the results means that we're 95% confident that they weren't due to chance. So we can reject the null hypothesis and accept the alternative hypothesis. If P is less than 0.01, that's significant at the 1% level. There's less than 1 in 100 chance that we would get these results if the null hypothesis was true. So we can be 99% confident that the results weren't due to chance, and we reject the null hypothesis and accept the alternative hypothesis. P less than 0.001 is highly significant at the 0.1% level, a chance of 1 in 1,000. So we're 99.9% confident that the results are not due to chance, and once again we can reject the null hypothesis. So if we've got a one-tailed test and we have a critical value here defined by the area under the curve in that tail corresponding to the significance levels, so for example if we've chosen 5% significant, p equals 0.05, we have an area corresponding to p equals 0.05 looked up in tables, and that tells us the critical value. If our value x is greater than or equal to the critical value, so it's to the right of the critical value in this distribution, or if our one-tailed test was postulating a smaller value, then it will be to the left of the critical value at the left-hand tail. If it's further away than the critical value, then the result is very unlikely to have occurred by chance. It's only a small probability in that tail, so we say that is very unlikely. We reject the null hypothesis. If x is less than the critical value, so it's to the left of the line in this curve, that result could easily have occurred by chance, so we can't reject the null hypothesis. If we've got a two-tailed test, we've got two critical values, and the critical values are defined by each area being half the significant level. So for a p.05 we want a total area of 0.05, so we need 0.025 in the left hand tail and 0.025 in the right hand tail to define the critical value. But if our value x is less than or equal to the lower critical value, or greater than or equal to the upper critical value, then that result is unlikely to have occurred by chance, so we can reject the null hypothesis. Remembering that for a two-tailed test we can reject if it is either bigger or smaller. On the other hand, if x is between the two critical values, this result could have occurred purely by chance, so we can't reject the null hypothesis. If we look at the possible test outcomes, if h0 is the null hypothesis and h1 is the experimental hypothesis, then in reality there are only two possible results. Either h0 is true or h1 is true, which means that h0 is false. But our experimental results could either be accept h0, which if h0 is true gives us a correct answer, or reject h0, which if h0 is false gives us a correct answer. But we could also reject h0 when in fact h0 is true. That is known as a type 1 error because it represents a false positive result. If we accept h0 but in fact h0 is false, that's a type 2 error, a false negative result. Let's look at these errors. The type 1 error is when we rejected the null hypothesis when in fact it was true. So we concluded that there was an effect by rejecting the null hypothesis when in fact there was no effect. That's quite a serious error, so we need to keep the chance of that happening rather low. The probability of this type 1 error is normally called alpha. So we need a low value for alpha, and we control that in our experiment by choosing a suitable critical value during analysis to keep alpha low. We'll come back to that in a moment. A type 2 error is the opposite. We've failed to reject the null hypothesis when it's not true. So we've failed to discover an effect that was really there. That's generally considered a less serious error than a type 1 error. The probability of this type 2 error is usually called beta, and we have to control that by a suitable study design. For example, by choosing an appropriate test and an adequate sample size, and we'll say a bit more about that later. So we've got these two errors, a type 1 and a type 2 error, to balance. The blue probability distribution shows the distribution of the test statistic if the null hypothesis is correct, and the green probability distribution shows the distribution of the test statistic if the alternative hypothesis is correct. And you see that they may well slightly overlap. So if we set a particular critical value of our test statistic, if the test statistic is to the right of that, we will reject the null hypothesis. If it's to the left, we will accept the null hypothesis. So the type 1 error is represented by the purple area where we reject h0 despite the fact it's under the blue distribution, so h0 is correct. And the yellow area represents the type 2 error because we accept h0 despite the fact that it's under the curve where h1 is correct. So we want to minimize both of those areas. Clearly the critical value will affect both alpha and beta. If we move the critical value to the right, it reduces the probability of the type 1 error but increases the probability of a type 2 error, and vice versa. So having the appropriate critical value is important. Now if the size of the effect is small, so the difference between the two means is small, then there is a large overlap of the two distributions, and so we're less likely to detect the effect because the probability of getting a type 1 or a type 2 error will increase. On the other hand, if we increase the sample size, that will reduce the width of both of those distributions, so the overlap will become smaller and we're more likely to successfully detect an effect. So If we have a small effect, we generally need a large sample size to distinguish it. But if we've got a large effect, we may be able to find it with a small sample size. Choosing the right significance level is important. The significance level is the chance of incorrectly identifying an effect that isn't really there. It's the probability of making a type 1 error, and we've already said that that is defined by the quantity alpha. And usually in statistics we choose an alpha or a significance level of 0.05, 5% significance. So we can use the probability alpha, normally 5%, to look up the critical value of the test statistic using the appropriate distribution. That will define the critical value of our test statistic, such that there is a 5% area to the right of it. Then for a significant test we just require the test statistic is greater than the critical value, or equivalently the p calculated from our test statistic is less than the significance value of alpha. There's also something called the power of a study we need to consider. Power is the chance that a study will discover an effect if it really is there. That is, we avoid making a type 2 error. Usually we require a fairly good power, and a power of more than 80% is quite traditional. The power is equal to 1 minus beta, so for a power of more than 0.8 or 80% we require beta, the chance of a type 2 error, to be less than 0.2. Now the power depends on various things. It depends on what test you're performing. It depends what level of alpha you've chosen, because reducing alpha also reduces the power, as we saw in the overlap of the two distributions. It depends on the size of the effect being investigated, because a large effect gives a greater power, is easier to detect. And it depends on the sample size, because a large sample size also increases the power, because it makes the distributions overlap less, and hence the difference is easier to detect. But you should calculate the power before you start a study. That's in order to ensure that it's worth doing. If you do the study and you don't have a big enough sample size, you will never detect an effect. If the effect is going to be too small so that you'll never get a big enough sample size to detect it, there's no point in starting the study. That is why in applying for ethics approval you're usually asked to calculate the power of your study to demonstrate that it is worth doing. So that's the end of part 2 of this talk on experimental testing. Will be continued in part 3.